Hi, in this video, we'll be continuing our study on linear transformation, and now we'll talk about the algebra or the operations that we can do on linear transformations. So what's important is that we realize that linear transformation inherits the structure of the vector space that it is mapping from V into W. And the set of linear transformation can also be proven to have more algebraic structures. Some examples of this include addition. So when you add two linear transformations together and you define it as so, it will still be a linear transformation, and when you scalar multiply them, it will also remain a linear transformation. You can then also prove that the set of now all linear transformation will be a vector space. So the proof that T and W are linear transformation when you add it together follows. So you define it as the following and see that by the definition it has to be T sending C alpha plus beta plus U bracket C alpha plus beta. And then this is a linear transformation, so you can expand it to this form. Similarly for this, and then you regroup it and you see that T plus U is a linear transformation as well. Same goes for showing that scalar multiplication remains a linear transformation, and this allows us to show that it's closed under both vector addition and scalar multiplication. So all you need to show is that the zero transformation is inside this set, and this will show that it is a vector space. Next, we shall prove that this set of linear transformation, if V and W are both finite dimensional, then this set is finite dimensional and it has a dimension of m times n. And to prove this is you can think of it as writing out the matrix, because it's a linear transformation from finite dimensional vector space. And this matrix has to be taking in n times 1 vector and then returning a m times 1 vector. So the matrix is like m times n. And because of this, you can already see that the standard vector is like 1 0 0 0 0 0 everywhere, and then 1 here and 1 here and the rest 0. So that's how you think of it intuitively, and the formal proof is writing it out in terms of having a basis and then what's the matrix that corresponds. And then you see that this matrix with this standard vector forms a basis for the set of linear transformation from V to W. Hence, this space will be finite dimensional and it will be a mn dimension. Now you let T be a linear transformation from V into W, and these are the coordinates of the vector T alpha j in the order basis B prime. Then we will now wish to show this follows. And this follows because you can just take U to be a linear transformation, and then for each j, U alpha j will be this following. So basically the idea is just to show that this matrix will be the linear transformation. And now we move on to showing that composition of two linear transformation is also a linear transformation. And that is so because ut bracket c alpha plus beta, we just need to do the t transformation first. So this will be, you can break it down into these two parts. And then because u is a linear transformation, you can further break it down. And then combining and simplifying, you get that this is equivalent to this. Hence showing that the composition of two linear transformation is also a linear transformation. Next, we already know what are injective and surjective functions, and what we now want to propose is that we say that T is injective if and only if the null space is the zero space, and it is surjective if and only if the range is W. So for the surjective part is very clear because it's by definition. For surjectivity, you need your codomain to equal to your range. And now for injectivity, why is the null space equals to the zero space? Well, if it's injective and we already know that the zero vector is sent to 0, then the null space must of course be the zero space. And if the null space is the zero space, then if you take tv1 equals to tv2, you just need to bring it over and it will be tv1 minus v2 equals to 0. So v1 minus v2 is in the null space, which means it has to be 0, which implies that v1 equals to v2, hence T injective if and only if the null space is the zero space. And because of this shows that we can show that the rank of a linear transformation is always less than or equal to the dimension of the codomain. And if the dimension of U is greater than the dimension of V, then the null space must be greater than 0, hence alpha cannot be surjective. If we let alpha now be a linear transformation between two finite vector space and dimension of U equals to dimension of V, then we have the following equivalent statements. And it is not hard to show why, which I'll leave it to you, as we already did the bulk. So we already shown that injectivity implies that the kernel or the null space is the zero space, so the kernel is 0, and because of that it already implies that the null space, the nullity is 0. And by the rank nullity theorem, this shows that the rank equals to the dimension of V, which implies that the image of alpha equals to V, hence alpha is surjective. And so what you really need to show is that surjectivity implies injectivity, and that can be shown easily from the basic knowledge of functions when their dimensions are equal, which is like saying that their cardinality can be the same. So I'll leave it to you to read it on your own how to prove that part. I'll now move on. So we now let alpha and beta be linear transformation and the dimensions all be finite. Then the dimension of the composition of function, the rank of this linear transformation, is now in between the rank of alpha plus beta minus dimension of V, which is the common one, and less than or equals to the minimum of the rank of alpha or the rank of beta. And why is this so? Well, the image of beta composed with alpha is just having beta restricted to the image of alpha, and so the rank of beta composed with alpha must be less than or equals to the rank of beta. And by the rank nullity theorem, this states that the rank of this function will be dimension of image of alpha minus away the nullity, which then has to be less than or equals to the rank of alpha, since this is the rank of alpha minus some positive number. So this shows that the rank of beta composed with alpha is less than the minimum of these two. And now we know that the kernel must be a subset of the kernel of beta, which implies that the nullity of beta restricted to image of alpha must be less than the nullity of beta, which equals to the dimension of V minus away the rank of beta. This gives that the rank of beta restricted to the image of alpha has to be equals to the rank of alpha minus with the nullity, since this is the rank of, which is larger or equals to now the rank of alpha minus plus the rank of beta minus with the dimension of v. Since this nullity is less than, so this has to be like the greatest. This has to be like the greatest subtraction that you can have. So anything else has to be greater than this. So then this shows that we just need to bring. This shows that the rank of alpha plus the rank of beta minus with dimension of v is less than or equals to the rank of beta circle alpha, which is less than or equals to the minimum of the rank of alpha, rank of beta. And a corollary of this is that if alpha is surjective, then if alpha is surjective, then the dimension of the rank of alpha is the dimension of v, so this cancels out. So this is length with the rank of beta, so of course, and then this sandwich in between that. So the rank of the composition is the rank of beta. And if beta is injective, well, then the rank of the composition is just the rank of alpha. By again using this inequality to help. And the last part of this video, we'll talk about invertibility, and that really comes down to saying that a function is invertible if you can find an inverse. And what is this inverse? Well, when we studied functions, we compose it from the left or compose it from the right, it results back in the identity function. So if t is invertible, then this inverse will also be unique from what we know from functions. And we can furthermore state, due to this property that we have, that if it's invertible, if and only if it's 1-to-1, and it's onto, and so when it's in finite dimension, saying that it's invertible is just the same as saying that it's injective, or it's the same as just saying that it's surjective, instead of showing that it's both, because they are equivalent. And so lastly, if we know that a linear transformation is invertible, and the inverse will also be down a linear transformation, that's not hard to show, and you can just see the steps over here for your own self-reading. But because of this, we say that now we have an invertible linear transformation from V onto W, and another invertible from U from W onto Z. Then this composition will also be invertible, and the inverse will now be T inverse composed with U inverse. And the last set of terminology to introduce is that we say that a vector space is isomorphic if there exists a linear transformation that is invertible between the two vector spaces. And if because of this linear transformation is invertible and so it's a bijective function, then V is a finite dimensional if and only if W is finite dimensional, and in this case the dimensions of these two will be the same. You can read the proof in the textbook, but I hope it's clear from the definition of an isomorphism. That's all for this video. I hope you have enjoyed it, and thank you for listening. Please like, share, subscribe, and I'll catch you in the next one. Bye.